Hi everyone, myself Jayasri and I belong to the Department of Electrical and Electronics Engineering of Rajgiri School of Engineering and Technology. Today I'll be starting with Module 6 of EE216 Electrical Engineering for Applied Electronics and Instrumentation, and today I'll be taking Part 1, that is 3-phase power measurement, and actually this is my 15th lecture for the series EE216. Now the topics that will be covered in today's lecture, we'll be having an introduction of star connection. You have already studied star connection and delta connection relevant to 3-phase. Now introduction to 3-phase power measurement. Before going into the details of 3-phase power measurement, let us see what is single-phase power measurement. And as today's topic is 3-phase power measurement, we'll be seeing 2 wattmeter method. And the variation of wattmeter reading with power factor will be discussing, and towards the end you will have a summary. Now you can see 3 waveforms. This represents a 3-phase supply system. What do you mean by 3-phase supply system? 3 voltages of equal magnitude apart by 120 degree. And you know, in India we are having a phase sequence RYB. What do you mean by phase sequence? The order or sequence in which different voltages attain their maximum value one after the other. And you can see R is reaching its maximum value first, followed by Y and followed by B. So in India we are following R, Y, B phase sequence. And since the 3 voltages are apart by 120 degree, I can write the 3 voltages instantaneous values as ER. It represents the first phase. ER can be written as EM sin omega t. EY can be written as EM sin omega t minus 120, and EB can be written as EM sin omega t minus 240. So now moving into star connection. So in star connection you are having the neutral. So what is phase voltage? Voltage between any line. We will be seeing into the details. Anyway, we just recollect what is phase voltage. Voltage between any line and neutral is called the phase voltage. We usually represent phase voltage by V subscript capital P. Now in a 3-phase system with RYB phase sequence, VRN, VYN and VBN can be called as a phase voltages, and these represents the RMS values of the phase voltages, and generally with respect to neutral. Now VRN, VYN and VBN, they are written according to double subscript notation. Now what is line voltage? Voltage between any 2 line outers. You already had studied 3-phase system in your basic electrical engineering in your first year. So what is line voltage? Voltage between any 2 line outers. So those can be represented by, so the 3 phases are RYB and we are following RYB phase sequence. So the first line voltage can be written as VRY, followed by VYB and VBR. So according to double subscript notation, we write 2 letters at the foot of the voltage symbol, VRY, VYB and VBR, and those represents the RMS values of line voltages, and line voltage is represented as V subscript capital L. So VP represents the phase voltage and VL represents the line voltage, and you already have studied line voltage is greater than phase voltage in your first year, and VL is equal to √3 times V phase, or else I can say that V phase is equal to VL divided by √3. That you have studied. Now you are having the current also. Whenever a load is connected, current flows through the load, and you can see the current flowing through each phase is represented as phase current, I subscript P, capital P, and the line current flowing through each line conductor can be represented as IL. And you already know the line current is same as the phase current. You can either write it as IL equal to IP or IP equal to IL. I am talking about the star connection because in 2 wattmeter method I have taken the star connection into consideration. Now star connection is otherwise known as the Y connection. Now we'll have an introduction of 3-phase power measurement, and you have studied 3 different kinds of powers as the apparent power, active power and the reactive power. Power actually consumed in a circuit is called the active power, and the power which flows back and forth is called the reactive power, and the total power can be called as apparent power or the complex power, which is represented by S bar. So S bar is written as P plus JQ if the load is of inductive nature, and S bar is equal to P minus JQ if the load is capacitive in nature. So that was an introduction. Power in an AC circuit can be measured by using an instrument called wattmeter, and the active power is represented by capital P, and in a single phase system it is given as VI cos phi, and the unit is watt. So an instrument which measures active power is called a wattmeter. And generally two types are there, electrodynamic or dynamometer type, which is the most commonly used one. We use wattmeters in our laboratories, and the most commonly used one is the dynamometer type. But induction type is also available, useful only when supply voltage and frequency are constant. So we generally go for dynamometer type. Now actually dynamometer type wattmeter directly gives the active power. In single phase it is P is equal to VI cos phi. Now coming to three phase, you are having two expressions like root 3 VL IL cos phi, or 3 times V phase I phase cos phi. Now in order to measure power is VI cos phi. So it has to measure the current aspect as well as it has to measure the voltage aspect and the phase angle between voltage and current. And we use a device called the wattmeter. We'll be studying into the details. So in order to measure the current, it has got a current coil, commonly known as the current coil, or it is sometimes known as the fixed coil, and it is represented by the notations ML. And M stands, you can see over here, this is my current coil. It is represented as a single loop because it has got less resistance. And M stands for the terminal which has to be connected to the supply mains. This is just a revision. And L stands for the terminal which has to be connected to the load side. So this represents my current coil ML. And you are also having the pressure coil which measures the voltage aspect. And pressure coil, commonly known as the pressure coil, it is otherwise known as the moving coil. Now it carries a current proportional to the voltage. Now since it has an inbuilt high resistance connected in series with it, we usually represent the pressure. In order to differentiate current coil and pressure coil, we represent the same with the help of a resistance. So CV represents my pressure coil. Now, so it is represented as a resistance. Same has an inbuilt high resistance connected in series with the coil. The coil is not shown over here. In some books you can see along with the resistance a pressure coil, so that the current through it is limited to a small value. So you have an inbuilt high resistance which limits the current through it to a very small value. So this represents the schematic represent for a dynamometer type wattmeter. So ML represents the current coil, CV represents the pressure. You will be seeing. So M and C will be generally joined like this, and C will be connected across, and ML being a current coil will be connected in series. Now before going into three-phase power measurement, you know the expression for power in a single phase system as VI cos phi, where V is the RMS value of the applied voltage and I is the RMS value of the circuit current. And this is a very simple arrangement which you have already done in your first year. So this represents my auto transformer. This represents my moving iron voltmeter which measures voltage, and you can see current measuring instrument connected in series with the load. So this is my moving iron ammeter, and this represents my wattmeter. So ammeter and ML, the current coil, they are connected in series. Voltmeter and pressure coil, they are connected in parallel. And this is my RL load, inductive dominating resistance along with a coil. So it is an RL load. So this is a very simple arrangement to measure the power consumed by an RL load. So this will give you directly the active power consumed by this one, and actually power is consumed in this resistance alone. So this represents my wattmeter, and since it measures active power VI cos phi, how do we write the specification? Voltage aspect, since it is single phase 230, you can write the range as 250 volt. Since the current is limited to 5 amps, you can write it as 250 volt 5 amps, and up to UPF, unity power factor, this can be measured. Okay, so V represents the RMS value of the applied voltage, that will be measured by this voltmeter. And I represent the RMS value of the circuit current that can be measured by the ammeter, and phase angle phi is between voltage phasor and current phasor, and all will be taken care by this device called the wattmeter. So this is a simple arrangement to measure single phase power of an RL circuit. And since the expression is P is equal to VI cos phi, how can power factor be computed? Power factor cos phi is equal to W, which is your active power, wattmeter reading divided by voltmeter reading and current. And being an RL load, power factor is incomplete with the term lag or late, so we add a term lag. Now we are going into the details of three-phase power measurement. So this represents, and let us consider this as an RL load. Z1, Z2 and Z3 are the load impedances. And actually three methods are there to measure three-phase power. Can be measured using single wattmeter method. In this diagram you can see 2 wattmeter. It can be measured using 2 wattmeters, and it can also be measured using 3 wattmeter. But what is a drawback with single wattmeter method? The load has to be balanced. Z1 should be equal to Z2 and Z3. But generally the loads are unbalanced, so you cannot generally go for single wattmeter method. Hence we go for 2 wattmeter method and 3 wattmeter method. Now the advantage of 2 wattmeter method over 3 wattmeter method is that we require only 2 meters. So we generally go for 2 wattmeter method, and it can be used for both balanced and unbalanced load, while 3 wattmeter method can also be used for balanced and unbalanced. So this represents a 3-phase load which is connected in star, and let us assume that Z1 not equal to Z2 and not equal to Z3. So will be, according to syllabus, you need to study only 2 wattmeter method, which is the most commonly used one. Can be used for both balanced and unbalanced load, and that too for star connection and delta connection. And for the time being I have taken a star connected load. So this is an RL load connected in star, and you are familiar with these notations: VRN, VYN and VBN. Voltage between this line and neutral is VRN. Voltage between this line and neutral is VYN, and voltage between this phase and neutral is your VBN. Now IR, IY and IB represents the current flowing through each load. So IR represents the current flowing through the first load, IY represents the current flowing through the second load, and IB represents the current flowing through the third load. Now in a star connected system, you know the line current. This is my line current, and that is same as the phase current. This can be treated as my phase current. So line current, there is only one and one path. So line current is same as phase current. Here also line current is same as phase current, and here also line current is same as phase current. So it is represented by IR, IY and IB. Now since the load is inductive, these currents lag behind their respective voltages by a phase angle phi. Since the load is inductive. Now let us look into the phasor diagram. And you know how to draw the phasor diagram. So first you need to draw the voltage phasors and voltage phasors of phase voltages. So VRN, VYN and VBN. They are all, being a balanced supply system, all the 3 voltages are equal in magnitude and apart by 120 degree. So angle between VRN and VYN is 120. Angle between VYN and VBN is 120, and angle between VBN and VRN is another 120. Angle around a point is 360. So this is 120, this is 120 and this is 120. So these 3 represents the phase voltages, and VRB, YB represents the line voltage. Now you can see one thing over here. This is my wattmeter W1, which is included in my R phase and Y phase. It can even be connected on R phase and B phase, or it can be connected in Y phase and B phase. The wattmeters can be connected in either 2 of the 3 phases. For the time being, I have connected W1 in R phase, and you can see the current flowing through the current coil is IR. Second wattmeter current coil is IY, and the first wattmeter pressure coil is connected between R and B, and the second wattmeter pressure coil is connected between Y and B. So this is W1 and this is W2. Now let us see the phasor diagram once more. Since B is common for both the pressure coils, so VRN, VYN and VBN, they are apart by 120 degrees. Since B is common for both the wattmeters, I can produce this backwards. So according to double subscript notation, I can rename it as minus of VBN. It is 180 degree out of A. So this is minus of VBN. Now the first wattmeter is connected between R and B. You can see the first wattmeter pressure coil is connected between R and B, and the second one connected between Y and B. So the voltage across the pressure coil of the first one is VRB, and the voltage across the pressure coil of the second one is VYB. So VRB, resultant of these two, I will be getting it as VRB, and the resultant of these two is V by B. Now if I produce this backwards, the angle between this and this is 60, and the angle between VRN and VRB is 30 degree. This is 60, so this much is equal to 30 degree. Now this is my current flowing through the R phase. So what is the angle between? The voltage between R and B is VRB and the current is IR. So you need to consider VRB and IR. So what is this angle? This is definitely 30 minus 5. Now for the second wattmeter, the voltage coming across its pressure coil is VYB and the current is IY. So I need to consider these two. I need to consider the voltage between Y and B, and I need to consider IY. So this angle is 60. So this angle is 30. So angle between VYB and IY is 30 plus 5. So let us see once more. The angle between VRB and IR is 30 minus 5. Considering the two wattmeters, how the two wattmeters are connected, and the angle between VYB and IY is 30 plus 5. So keep that in mind. We need to consider this angle as 30 minus 5, and we need to consider this angle as 30 plus 5. So that is whatever I had told you is mentioned over here. Now the phase angle between VRB and IR is 30 minus 5, and the phase angle between VYB and IY is 30 plus 5. I have already explained. Now the first wattmeter measures a voltage between VRB. So its voltage can be written as V subscript RB. The current flowing through that wattmeter is IR. And what is active power? V into I into cosine of the phase angle between these two. So it is 30 minus 5, cos of 30 minus 5. Now VRB is your line voltage, and in star connected system IR can be treated as your line current or phase current. Now I am considering it as this, since this is line value, I am considering this as a line value. So VL IL cos 30 minus 5. This is with regard to the first wattmeter. Now let us consider the second wattmeter. Its pressure coil is connected between Y and B. Y and B means it is your line voltage. IY can be treated as your line current or phase current, since this is the line value. So IY can be treated as your line current, and the angle between VYB and IY is, we already seen, 30 plus 5. So the included angle between this and this is 30 plus 5. And so what is power? V into I into cosine of the phase angle between these two. So it is VL IL cos 30 plus 5. Now let us add W1 plus W2. So VLIL cos 30 minus 5 plus VLIL cos 30 plus 5, and doing the simplification. Since VL and IL are common, I can take that out. So VLIL into cos 30 minus 5 plus cos 30 plus 5. This is of the form cos A minus B. What is cos A minus B? Cos A cos B plus sin A sin B, and this is of the form cos A plus B, cos A cos B minus sin A sin B. So expanding, VLIL cos 30 cos 5 plus sin 30 sin 5 plus cos 30 cos 5 minus sin 30. So these two will get cancelled, and W1 plus W2 can be written as VLIL into 2 times cos 30 into cos 5. And what is cos 30? It is nothing but root 3 divided by 2. So 2 and 2 get cancelled. So you are getting root 3 VL IL cos 5. And you already know this is nothing but the expression for active power for a three-phase system. So root 3 VL or you even have 3 V-phase I-phase, but the first expression is considered root 3 VL cos phi, and that is your expression for active power for a three-phase supply system. So we have seen W1 plus W2 represents the total active power consumed by a three-phase load, and we had taken the case as an RL load. So in 2 wattmeter method, you need just add the 2 wattmeter readings, and what you get is the total active three-phase active power, which is equal to root 3 VL cos phi, and smaller unit is watts and higher unit is kilowatts. So the basic thing is that W1 plus W2 will directly give you the total active power consumed by a three-phase load when it is connected in star. You will also find that you get the same expression if the load is connected in delta also, but time being I will be taking only for the star connection. So we had done the operation W1 plus W2. Now again the same wattmeter reading. Now what I am doing is W1 minus W2 and see what you are getting. So the same thing, VLIL cos 30 minus 5, but here subtraction, VLIL cos 30 plus 5. Doing the very same operation, VLIL being common taken out, cos 30 minus 5 minus cos 30 plus 5, expanding the same, you will be getting VLIL cos 30 cos 5 plus sin 30 sin 5 minus cos 30 cos 5 plus sin 30 sin 5. These two will get cancelled. So you are getting VLIL 2 sin 30 sin 5. And what is sin 30? It is half. So that 2 and this 2 get cancelled. So you are getting VLIL sin 5. In three-phase system, total reactive power is actually root 3 times VLIL sin phi, but on subtracting W1 minus W2 you are getting only VLIL sin phi. So what is the total reactive power? So W1 minus W2 has to be multiplied by root 3. So subtract the wattmeter readings and multiply by root 3, you get the total reactive power in a three-phase system. So Q, you know, reactive power is represented by Q. So Q is equal to root 3 W1 minus W2, and the unit for reactive power is volt ampere reactive. Higher units we will be writing it as K, small k VAR. So W1 plus W2 is the total active power, but total reactive power is, you have to multiply it by root 3 and take the difference, W1 minus W2. So we have done with the expression for total active power and total reactive power, and since you are having 2 wattmeter reading, you are in a position to compute the power factor cos phi. Now let us consider the power triangle. You are familiar with the power triangle. Since the load is RL load, this represents a shape which lies in the first quadrant of the complex plane. So this represents my power triangle, active power or real power, true power, reactive power, and this is my apparent power, this. So this represents a right angle triangle. Now tan phi is opposite side by adjacent side. So this is my reactive power, which is given by root 3 into W1 minus W2, and the active power we already seen, P is equal to W1 plus W2. So what is phi? Tan inverse root 3 into W1 minus W2 divided by W1 plus W2, and this will give you phi. And in order to get power factor, cos of that angle has to be considered. So cos phi is cos of tan inverse root 3 into W1 minus W2 divided by W1 plus W2, and you have to attach the term lag or lead. If it is an RL load, lag, and if the load is capacitive in nature, you add the term lead. So in this case I have taken RL load, so the unit is, power factor is lag. Now you have seen how power can be active power, reactive power, and power factor can be computed using 2 wattmeter method. Now variation of power factor reading with wattmeter reading with power factor will be discussing, and the loads can be purely resistive, it can be purely inductive, it can be purely capacitive, etc., etc. RL load, RC load, etc., etc. So first case, let us see when the load is purely resistive. Purely resistive means the phase angle between voltage and current is 0. So phi is 0 means power factor is unity. Now W1 VLIL phi 0 means VLIL cos 30 and W2 is actually VLIL cos 30 plus phi 0. So you get VLIL cos 30. So cos 30 is root 3 divided by 2. So W1 is root 3 by 2 VLIL and W2 is equal to root 3 by 2 VLIL. Both the wattmeters, you can see these two are having equal magnitude. So it will show same reading and both will be positive. So when the load is purely resistive, keep in mind these two are of equal magnitude and they will show positive reading. So the total active power P is equal to W1 plus W2. Now let us take the case when the load is purely inductive. Load is purely inductive means the phase angle between voltage and current is 90. Cos of 90 is 0, so power factor is 0. So angle is 90, so W1 is VLIL cos 30 minus 90 and W2 is VLIL cos 30 plus 90. So this on simplification you are getting it as cos 60. So half VLIL and this is cos 120, it is minus 1 by 2. Cos 120 is minus 1 by 2. So W1 is half of VLIL and W2 is minus of half VLIL. Both the readings are of equal magnitude but with opposite sign. So first one will show you a positive reading and the second one will show a negative reading. Now the total active power is these two of equal magnitude but in opposite sign. So what happens to my total power? That comes at 0. And you already studied in your first year power consumed by a pure inductive circuit is 0. And that has been proved over here. Now when the power factor is 0.5. If the power factor is 0.5, what about your phi? Phi will be 60. So substitute for phi over here, W1 is VLIL cos 30 minus 60 and W2 is VLIL cos 30 plus 60. This comes to cos 90 and you know cos 90 is 0. So W2, what does it show? Cos 90 is 0 means your wattmeter reading W2 will show a 0 reading and the wattmeter W1 will show what is cos 30 root 3 by 2. So it is root 3 divided by 2 VLIL. So W1 will show a positive reading and W2 will show a 0 reading. So what is your total active power? Total active power stands as W1 alone since this is showing a 0 value. Now let us have a summary of what you have studied. You have seen several cases and unity PF, equal readings, both positive. 0.5 just now you have seen unequal readings, one wattmeter showing a positive value and the second wattmeter showing a 0 value. And suppose the power factor is between 1 and 0.5, say 0.8. Both will be unequal readings. W1 and W2 will show an unequal readings and both will be showing positive. So what is your total power? P is equal to W1 plus W2. Now power factor 0 means purely inductive and it can also be purely capacitive. So equal readings but with opposite sign. So what is your net power? Net power will be 0. Now the last case between 0 and 0.5. You will have unequal readings with one showing a positive value and second wattmeter showing a negative value. So this is a summary of 2 wattmeter method. Now these two are the reference books. Basic Electrical Engineering by DC Kulkshetra, which you might have referred for studying first year, Basic Electrical Engineering by DC Kulkshetra. And the second book is actually volume 1 of B.L. Tereja and A.K. Tereja, a textbook of electrical technology, volume 1 by B.L. Tereja and A.K. Tereja. And thank you.